Hello everyone and welcome to this series of lectures on digital system design. In the previous set of lectures we had looked at the general idea of how we go about modeling digital systems in a way that we can actually simulate their behavior and sort of motivated the idea of why we need hardware description languages, the common ones being Verilog or SystemVerilog and VHDL. Now as discussed there, we are going to be using Verilog a lot more in this course. And so right now what we are going to do is go a bit deeper into many concepts of Verilog. Now one thing I want to emphasize is that when I say Verilog in this context, I use the term interchangeably with SystemVerilog. Yes, there are differences between them. Verilog and SystemVerilog are not completely equivalent. SystemVerilog can in general be seen as a sort of superset of Verilog, but on the other hand there are places where modeling something in Verilog requires you to think a little bit differently than how you would in SystemVerilog. For the most part, I'm going to be focusing on aspects that make the design that you are creating synthesizable, and therefore we'll be focusing on a fairly limited set of either language. So when I use the term Verilog, please understand that in most cases it's being used interchangeably with SystemVerilog. The biggest place where that becomes obvious is, for example, the use of the term logic instead of the reg or wire in order to declare signals. But apart from that, there may be a few other subtle differences as well in terms of how we use certain kinds of constructs. Right? For the most part, as a new learner to the language, you should probably focus more on SystemVerilog than on Verilog. Pretty much all simulators as well as synthesis tools have fairly good support for SystemVerilog at this point in time. So there's no real good reason to go with the older versions of Verilog as of now. And the additional features that SystemVerilog provides and also some of the safety capabilities make it worth the transition, if at all there is a transition that you need to observe at that point. Okay, with that in mind, let's get into the details of some of these lectures. We are going to start by talking about how we would do logic modeling in Verilog in the first place. So what do we mean by logic values? What would a basic module look like? And what does the idea of propagating values in Verilog code mean, and how do we basically need to understand it? So as we already discussed, digital systems are essentially dealing with truth values, right? And true or false interchangeably used with 1 or 0, actually not 0 or 1. So typically true is mapped to 1 and false is mapped to 0, although as you as is hopefully clear by now, that's just a convention. There was nothing really preventing everyone from saying, okay, true corresponds to 0 and false corresponds to 1. That's also perfectly valid. It would have resulted in a slightly different set of equations, right? But it's just that every single equation would change correspondingly because it's just, after all, a term that we use. In our case, of course, true is generally conventionally mapped to 1, false is conventionally mapped to 0, and all the rest of the equations that we sort of follow based on the Boolean equations and so on are based on that assumption. Okay, now we have these Boolean values, and the whole Boolean algebra is defined around these values and these concepts. Now in reality, right, at the end of the day, when you want to build up circuits, the physical world kicks in, right? And what ends up happening is that you need to deal with some additional possible values that can come in. The practical matter is that 0 typically corresponds to a low voltage, ideally the ground voltage, and 1 typically corresponds to a high voltage, typically the supply voltage. But voltages are not discrete. You don't jump between 0 and VDD abruptly. You can actually go to all the stages in between, and sometimes you may even have marginal overshoots or undershoots, right, into the negative territory or above VDD. So that's one aspect that needs to be thought about. That's typically beyond the scope of logic simulators, right? Logic simulators don't really try and model the analog values that are present in between 0 to VDD. But instead there are still a couple of unknown values that you do that you would like to model. One of them is the so-called X, or the don't care, right? A don't care essentially indicates that I don't care or don't know, right? A don't care is usually used in truth tables or in the Karnaugh map in order to indicate that this is a particular set of input combinations for which we don't care what the output is. In the context of logic modeling with Verilog, it's actually more of a don't know rather than a don't care. So what you are saying is that an x is an unknown value, right? And you use this in order to say that if I have not specifically initialized a particular signal to either 0 or 1, there is no way that I can predict in general when I switch on the system whether it is going to be 0 or 1. And this is an actual practical matter, right? When you switch on a system, there is no guarantee that all signals or all wires are going to be 0. We very often assume that that must be the case because after all 0 corresponds to a low voltage, and if you have not applied a voltage, how could something be at a high voltage, right? That's not how it works in practice. Very often what can happen is there are capacitances inside a circuit, which means especially that if you sort of switch off and switch on again very quickly, there's every possibility that a particular wire somewhere inside the circuit is actually still holding a logic 1 value, right? So the only correct way to deal with it is to actually say that unless something is explicitly initialized or connected to 0 or to ground or to the VDD, we don't know what its value is, which means that every circuit must be explicitly initialized, right? From the digital systems course, you would probably know about what the reset conditions are, right? You typically, what we do is we bring in a separate signal that we call a reset signal and connect that to all the state related variables, the memory or the flip-flops that are present inside the system, right? And say, okay, now when the power is switched on, I will ensure that this reset signal is held active for a certain amount of time. How do I do that? Well, that's an external input. I could use a button, I could use some kind of circuit that basically holds a signal high for a certain amount of time and so on, right? But that reset is then responsible for ensuring that the entire internal state of the system is brought to a known set of values. Without that, in general, you need to be able to deal with x. There is one more possible state for a signal, which is what is called the electrical isolation or a high impedance state. This essentially corresponds to a scenario where there is a wire. The wire is probably connected through a transistor or a switch to either VDD or to ground, but the switch itself is inactive, which means that for all practical purposes, it's an open circuit, right? You have something which basically looks like there is, let's say, a voltage source, there is a switch, and there is some potential out here, right? So what I can say is when the switch is closed, right, I can say that the voltage V1 at this point is going to be equal to the voltage at Vs. But when the switch is open, I really cannot say what the voltage at V1 is going to be, right, because it's not connected anywhere. That is the so-called floating state. It's not connected. In general, what we say is we also call this a high impedance state, and the reason for calling it high impedance is that this connection can actually be thought of as something which is potentially a connection but is currently in a high impedance state. There is no way that a current can flow through here, and because a current cannot flow through, we cannot say that V1 is equal to Vs, right? It turns out that this kind of high impedance functionality is actually fairly common and is used in a lot of circuits, especially in the context of multiplexers and buses, as we will see later, which means that it's also something that you probably want to model when you are actually looking at digital circuits. So the bottom line is Verilog as a language uses the so-called 4-valued logic. Ideally, we would like to use only zeros and ones, but they also bring in a concept of x as an unknown and z or z, or sometimes it's called a high z or something like that. So I'll be using the term z or z interchangeably over here, right? 0, 1, x and z are the 4 values that are used in order to indicate the different possible states that a signal can be in. Okay, now we have talked about a Verilog. You have probably already seen a couple of examples of what a Verilog program looks like, right? As I already mentioned, the word program is probably inappropriate, right? These are not really programs, and the reason I'm stressing on this is you should not think of them as programs, right? It is much better to think of these as chips on a breadboard. Every module, rather than thinking of it as a function that can be called, it is much better to think of it as a chip on a breadboard that's connected up through wires to various other chips and is always active, which means that whenever any of its inputs changes, potentially I'll need to go in and see what happened inside the module as a result of the changes at its inputs. And as a result, it might end up changing its outputs, which in turn will influence other chips that are connected on the breadboard or other modules that are connected in your Verilog code. So an example of what this would look like is that it essentially has a very straightforward structure, right? What we see is that there is, for example, this thing out here which is the word module, right, which is a keyword. So there are a number of module keywords that exist in Verilog. Module is one of them, assign is another, end module is the corresponding matching keyword as far as the module keyword is concerned, right. There are inputs, outputs, wires and a few others that you will come across as we go forward, right. And the point is that these keywords are used in order to structure the program. Just like in C programs, you would have void, which is the function type, then you would have the name of the function, then you would have the parenthesis within which the argument list, the set of parameters being sent into the function are present, right. Then the curly brackets, which basically ensure that the scope of the function is defined. Verilog uses a slightly different setup. You do have the keyword module explicitly, unlike the void. You don't have a function return type. Every module is just a module in Verilog, right? So there is no output return type here. And the reason for that is Verilog modules can often return multiple values. In fact, the word return itself is wrong in this case. They have multiple outputs, right? So they can have inputs and outputs that are explicitly defined out here. There has to be a name associated with the module so that you can then refer to it in other parts of your code. You give the set of inputs and outputs, the parameters, the ports as they are called, right. So these are called ports as opposed to function arguments in a C or Python like programming language, right. The order of these parameters does matter, right, and what we will see later is that in order to avoid this issue with the order mattering, we actually use something called named instantiation, where we explicitly sort of have a mapping between the name given over here and the name of the signal that we want to connect it to, right. The reason for that is because unlike in C, where you typically have functions with a small number of parameters and a single return value, very often in Verilog you have a very large number of ports associated with the module, multiple inputs, multiple outputs, right, potentially even the so-called inout kind of port, which is rare and ideally you shouldn't use unless you are very clear about why you are using it, right. But the point is that the number of ports in a Verilog module is typically significantly larger than the number of arguments that a function in a language like C or Python would have. Therefore, the idea of just sort of putting down the list of parameters in sequence doesn't always work out in practice. It's always better to have this kind of named instantiation, as we will see later. Another thing that you might observe is you have comments, right, and this just looks like C, or to be more precise C++, because we use a / notation. The /*/ just like in C is also accepted for Verilog, which sort of tells you, Verilog's origins are related to C in some sense, right, and even in terms of how the language looks and the simplicity of the overall code, there are a lot of similarities to C. That should not sort of trick you into thinking that knowing C means that you understand Verilog. There are some really true fundamental differences between them that you really need to watch out for. Okay, so you can insert comments anywhere, either an entire line or pretty much anywhere on a line, and then everything after that until the end of the line is considered a comment. There is this notion of so-called wires, right. These are made for internal connection. So essentially what happens is I have declared a wire A, a wire B, wire Y1, wire Y2, and in this case they are directly inputs or outputs. There are no intermediate connections out here. But very often wires are used for making intermediate connections. And this is a case where you have to be very careful, right, and is in fact a common source of bugs in Verilog code. If you have not declared a wire explicitly, so you do not have a statement saying wire X, but you happen to use X somewhere out here, or either on the left hand side or on the right hand side, in a language like C that would immediately be an error because it would say undefined variable, right. In a language like Python, that's not the case, because in Python you can implicitly define a new value and just go ahead with it. In the case of Verilog, it's if anything even worse than both of these conditions, right. Of course, the first condition, what C does, is probably the right thing to do. You force somebody to declare a variable or a wire name before using it. In Verilog, what happens is it implicitly assumes that there is a wire. More importantly, it assumes that it is a 1-bit wire, right? And the reason why that's dangerous is because very often by having something implicitly declared as a 1-bit wire, the width of ports can themselves get changed without your even realizing that something like this has happened. So there are sort of directives that we can give to the compiler to tell it to warn us, but this is something that you have to be very careful about when you're writing code in general, right? It is a potential source of bugs, which unfortunately is just a feature of the language. It's not much you can do about it. Okay, so what happens when we have got some code in Verilog? And this is an example of what a Verilog module looks like, right? And this example is basically used in order to show what happens in the context of so-called propagation of values. Right, what we are saying over here is I have a module, it has a name, it has certain inputs, it has an output, and now I have a couple of different wires that I have declared for internal connections, right? Remember, as I said, if I had not declared this line, right, the program or the code is still valid, and implicitly in this case it would actually have worked fine because temp1 and temp2 are anyway single bit values, right? So it would go ahead and assume temp1 is a single bit value, perform this computation a ampersand b, temp2 is another 1-bit value, it would go ahead and do this and it would compute this value as well. So everything would actually have worked out fine, right? But if, for example, a or b was, let's say, an 8-bit value, and I had forgotten to declare the wires out here as explicit 8-bit values, it would go ahead and assume these are 1-bit values, perform computations and probably end up giving you the wrong result, okay? But now let's think about what's actually happening out here, right? If I think about this program, the way to look at it is I have a module which has 3 inputs, I'll call them A, B and C, and now the question is I'm performing some computations with them, right? The first one is the AND operation, right, and this basically comes out as temp1. Okay, what do I do after that? I take temp1, I OR it with C, okay, and I get temp2 as the result. And finally what I do is I negate that and I get Y. So as you can see, this code that's written over here exactly corresponds to this diagram that I have drawn out here. Now comes the question of what exactly do we mean by value propagation, right? And the way to think about it is I have my inputs out here, okay, and anytime there is a change in the value of either A or B or C, I need to then go in there and find out what kind of an effect is this going to have. Now the way that the code is written is actually, perfectly matches with how we would evaluate in practice. What we would say is, okay, you need to go in there and look at this value A ampersand B, compute that, right, and we get temp1 as a result. After that, right, so there is a notion of sequence, I compute temp1 ORed with C, and finally I compute the NOT of temp2 and assign it to Y. So this sequence matches very well with what we would see in a language like C or Python, right? And any time that there is a change in A or B or C, I would need to go through this entire sequence and perform these computations. Now the interesting thing, what you need to keep in mind over here is, as far as Verilog is concerned, and we'll be seeing more examples of this later, these 3 assignment statements are, in principle, they could be executed in any order. There is nothing fundamentally forcing you to do it from top to bottom. So it's quite possible that I first go in there and look at this assign statement. Why would something like that happen? In order to understand that, you need to go a bit deeper into how scheduling of events in Verilog happens, or scheduling of processing happens, right? And we'll be talking a little bit about that in a later part of this series of lectures, right? But the bottom line is that because of the fact that there is nothing fundamentally forcing you to do it from top to bottom, it is quite possible that you might end up looking at this statement first, or more importantly, you might even write the code so that this statement goes first. You can reverse the order of these 3 statements and you will get exactly the same result as we see over here, right? That's the important thing. Now why does that work? It is because anytime there is a change in A or B, it goes in there and computes A ampersand B, assigns that to temp1. Now it sees that there is a change in temp1, that in turn triggers this and says, okay, now I probably need to go back and recompute temp1, right? If there was a change in C, then okay, it will take that as well as C and compute both of them together, right? And then finally, when it sees that temp2 changed, it then needs to go in there and once again recompute the value of temp2. So all of this is entirely possible. You could have it happening in any sequence, and the fact that these values sort of propagate down these wires over here and finally they come out at the output is essentially the entire model underlying how Verilog is simulated and what its functionality means. Okay. And this is the basic part that you need to understand as far as modeling something with Verilog is concerned. What exactly does it mean to write modules in a certain way, and how would it get evaluated as you go through? Now, remember that we said there is also the possibility of a so-called X, right? What happens in the context of X? What if one of these values, right, either A or B or select, which are the inputs over here, turned out to be X? And in order to understand that, we need to first think of what this module actually corresponds to. What we are saying is that this is a multiplexer where this is select, this is A, this is B. Now, how do I know this is a multiplexer? Because of this notation, essentially it corresponds to a multiplexer, right? And keep that in mind, this notation by itself is just the so-called ternary assignment operator in Verilog, similar to the thing in C. The fact that it corresponds to a multiplexer is an observation we have made. It's not a fundamental rule of Verilog. Verilog does not say that this is actually a mux. All it says is this is a ternary operator. I am drawing a mux because that is our normal interpretation of what a statement like this looks like. Okay. Alright, so with that in mind, now what if this is 0, this is 1, and let's say this is 1, right? What it basically means is that I can say that this path is going to get activated, right? The one which passes from B to the output, okay? But the question becomes, what happens if instead this was unknown, right? Then basically what do we have out here? We could potentially end up with, we don't know what happens out here, right? The moment this becomes X, right? Because I don't know if this path or this path is supposed to get activated. So the only thing that we can do is this also becomes X. It's unknown, right? On the other hand, what if I had something like this? 0, 1, select is equal to, let's say it's still 1. B happens to be 1 and A happens to be X. In this case, it's actually safe for me to say that B is the output, Y is equal to 1, right? It's not X in this case, and the reason it's not X is because I know that the path being followed is this one, right? I don't care that this part over here is unknown. This effectively overrides the unknown value that I see over there and comes out cleanly saying that okay, this should be the value that I see at the output. Now, this basically becomes a question of how we interpret, how exactly is the thing implemented. It's potentially possible that depending on how a multiplexer was implemented internally, this may not even hold true. But propagating X's and sort of saying, okay, do I know what the final output is going to look like, right, is something that simulators need to be able to do properly in order to identify potential problems with our code. So, one question which I just want to briefly address, I already talked about it a little bit, is why do we even need the X value? It essentially corresponds to either unconnected ports or signals, things that have not been connected properly, or to power up initialization. As I said, when you switch on a system, you do not know whether the outputs of registers are zeros or ones, right? They could be either one of them. They will typically be either 0 or 1, they will not be sort of floating somewhere in the middle because they are registers after all. But is it actually a 0 or is it a 1 is not guaranteed unless you have taken steps to explicitly initialize. So the simulation can actually help to propagate these, and very often it can help to debug problems with uninitialized values, right? Now, having said all of that, it is in some sense a limited kind of functionality, right? I mean, we ideally should not need to model debugging based on whether or not we are able to propagate X values, right? Because we should be ensuring that every part of our circuit is initialized properly to start with. And because of that, there are some simulators, well-known simulators even, that do not follow the full 0, 1, x, z kind of 4-valued logic and instead just stick to 2-state simulation. The most well known of those is something called Verilator, which is an open source simulator, which is actually a very powerful simulator. Because of this simplifying assumption that it has over here, it actually ends up being even faster than many commercial tools for fairly large circuits, right. Of course, this is a fairly big limitation if you actually need to have the unknown value propagation, but as I said, there are design methodologies that will avoid that problem arising in the first place. And so it is something to be aware of, though, that not all simulators automatically propagate excess the way that you would expect. Right, and the fourth value of the 4-valued logic is the so-called high impedance, or the Z state or the Z state. Okay. This is an example, right. Basically what we have over here is there is a module with two inputs, data and enable, and an output called out. And what we are saying is whenever the enable signal is high, this should become data, but when it is not high, that is when the enable signal is low, this basically goes into a high impedance state, right. The typical sort of functionality looks something like this, the kind of circuit that is, or this is the schematic that is used for this, right. And what it says is whenever enable is high, the output is equal to data, but when enable is low, it is effectively as though you have just cut this connection off. Now why is that a nice thing? Because it basically allows you to also have yet another thing out here with another enable, I will call it EN2, another data which I will call D2, and I can just short these two connections together, provided that the condition is EN2 and enable should never simultaneously be 1, right. Under that condition, we can ensure that at any given point in time, this Y that we have out here is being driven either by data or by D2, but not by both at the same time. So any possible chance of a short circuit is removed because of the fact that if enable was 0, this would be in a high impedance state and therefore no current can flow into it. If EN2 was 0, this would be in a high impedance state and therefore no current could flow into it. If both are high, that is a problem. You need to ensure that that can never happen. If both are low, that is not really a problem. All it means is this will also be in a high impedance state. Okay. This turns out to be a fairly common occurrence actually in practice, right. The whole idea of how buses are created in fairly large circuits is based around this idea that you can safely short outputs together if they are in the Z state. Okay. Now of course, when you are actually constructing the circuitry out there, you are not just modeling it as some kind of a Z state in Verilog, you actually have some kind of explicit notion of switches and high impedance states. This is a way of modeling it. And of course, the actual model that we need to do is a full electrical model that tells us what is the impedance and what is the amount of current and whether there is a possibility of damage and so on, right. Verilog just simplifies all of that and allows you to sort of say, okay, assuming that somebody has taken care that the high impedance is actually high enough impedance to ensure no current flows, this is how the functionality will actually work. One common place where this actually comes into practice, to implementation in practice, is in so-called inout ports, ports that can behave either as inputs or as outputs depending on certain conditions. That condition is essentially captured by the enable signal, which says either this port is an output and can drive values onto the bus, or it acts as an input and basically receives values coming in from the bus, right. So you need a lot of care when designing such inout ports. So at least to start with, I would strongly suggest simply do not even think about inout ports in Verilog. Just forget about the fact that they exist. You should not be using them unless you are extremely clear about why and under what conditions they are going to be active. So with all of this in mind, essentially what the Verilog code does is it helps us to model it. But in order to actually see whether it's working the way that we expect, we need to be able to simulate this code or to interpret the Verilog code. This is essentially where the semantics of this language comes in, right. This is very similar to the idea of other programming languages. Now in a language like C, we don't usually talk of simulating the language, because after all what we do in C is we take the language, the constructs that we have, and convert them into a machine language which directly runs on the computer. In some sense that is also a simulation. All that it's doing is it's converting it into another language that the computer actually knows how to natively run. You might have at some point worked with virtual machines, right, either in your whatever operating system you are using, right, or in some other context where you might find that the code that you are writing is actually not directly running on the processor, it's actually going through something which is interpreting your code, right. Common examples of this, one of them is if you write anything in the Python language. Another one is, some of you might have seen that there are many web apps that are built around the so-called WASM, WebAssembly, right. And what WebAssembly does is it basically provides a kind of neutral language which is a virtual language. It allows you to write code in JavaScript or in any other language, convert it into WebAssembly, and that will then get interpreted very fast usually on the browser that you have and is going to run like a proper language. The point is Verilog also works in a somewhat similar way, right. You can take your Verilog code and convert it into some kind of an intermediate representation that can then be interpreted, and all of these operations that we said, should a 0 be propagated, should a 1 be propagated, should a particular statement be re-evaluated, is there a new sort of value that needs to get propagated from one place to another, all of that gets handled by the interpreter. So, like I said, it is similar to other programming languages. The big differences are that the notion of concurrency and an explicit notion of time are also brought in to the language, which do not exist in most programming languages. So, with all of this in mind, I am going to show an example of a simple Verilog code, right. And so, as you can see over here, this essentially corresponds to an example of what a Verilog code might look like. It's a very specific kind of code, right. What we have over here is it's a module. I've given it a name, but you will notice that it has no parenthesis after the name. It has no inputs, it has no outputs. It is a so-called test bench, and we'll be talking more about it later. On the right hand side, we have the main module that's actually being simulated. So you have a module, it has a name, it has inputs and outputs, and it has some functionality inside it, right. And what we have over here is we are actually going to sort of put this module directly in place and then see what happens as we sort of go through the different functionality, okay. We'll be talking more about test benches in a moment, but for now I just want to use this in order to demonstrate the ideas of how a particular simulation might work. The simulator will basically need to go through and look at the test bench. Inside the test bench, it finds that there is a reference to this other module called value demo, which is what we have on the right hand side. So at some level you can think of it like, is this like a function call? Well, no, as I said, it's not like a function call because it's not as though you're calling this function once, evaluating it and being done with it. It's more like you're taking this particular value demo as a chip, putting it on a breadboard, and all these other wires and registers are connected up to the setup that we have out here, okay. And this initial block that we have over here, which once again is something we'll be talking more about, is something which actually tells us, okay, what are all the different things we need to feed in to this different set of inputs, okay. A couple of things I want you to observe. There is also a notion of something called a reg, right. This is one of the more confusing aspects of Verilog, and in fact SystemVerilog sort of does away with it, right. A reg is something that can be assigned inside a procedural block. What is a procedural block? It's either this thing which starts with initial or something which starts with another keyword which is always, right. Anything that you want to assign, a value that you want to assign, like A is being assigned a value, B is being assigned a value, select is being assigned a value, all inside this initial block. So they need to be declared as registers or reg, right. Very often people mistakenly assume that this means they are flip-flops. They are not. There is absolutely no guarantee that something declared as a reg over here will get converted into a flip-flop in hardware, right. This is a very important fact you need to keep in mind. In order to actually derive a flip-flop or to create a flip-flop in hardware, there are explicit language patterns that you need to put in place, right. We'll be seeing more of those later. For now, the important thing to keep in mind is declaring something as a reg or a wire over here has more to do with how it can be used in the rest of your code. You will notice that the wires are being used in order to basically get the outputs from the module that you have put, whereas the reg values are being used so that they can actually be assigned values in our test bench itself, okay. Like I said, SystemVerilog does simplify this by removing both of these concepts and just replacing it, or not removing, but bringing in another notion of something called logic that can replace both of these with a single keyword. Okay. For the most part, we will be switching over to SystemVerilog. The reason why it is important for you to be aware of this is because even now it is very likely that you will come across various forms of legacy code that still use the reg and wire formulations, right. So you should at least be aware of what they are and how they can be used in case you come across such code. Okay, so what does a module in Verilog look like? I first instantiate whatever I am trying to test, and then I start applying varying sets of inputs to it, right. So I can, for example, set the value 0, 0 and select equal to 0 to the inputs, and it will show me what the outputs are going to be. I can change the input, right, from select equal to 0 to select equal to 1, and I should be able to see what happens to the output. I can also test by putting in some kind of other things which basically show me what happens with some high impedance, right. And in order to actually understand what's going on in here, I will actually need to go into this value demo and see that it has 3 outputs, y1, y2, y3, and one of them is basically the ampersand of both of these, so it's basically ANDing them together. Y2 is either sending out the value of A or putting it into a tri-state mode. Y3 is either sending out A or putting it into an unknown mode. And all of this can be simulated by basically clicking on this run button out here. And what happens is this gets basically simulated. This is on the edaplayground.com website, right. Of course, you can run it locally also on your systems using the, in this case, the simplest thing to do will be to use the iVerilog Verilog simulator, because that's what is being used even on EDA Playground, and there will be more information about that when you need to run such code. So what ends up happening is this initial block basically goes through and prints out all of these values which are there in the $display, right. And as you can see, various things like, for example, what happens, how does a Z get propagated, how does a X get propagated, what are the conditions under which each of those different things comes through, all of that can be seen as part of this test bench.